When we went out to look for molecular gas in this search catalog, we were thinking that if we got like, 4 or 5 clouds out of hundreds, we'd be happy. We found nearly 200. There was more molecular gas up there than anybody had imagined, and they became the MBM clouds.
In physics, we sometimes make the mistake of asking why, when really we should be asking how. We're categorizing things. We're explaining processes. We're not explaining origins or why it's this way and not another way.
Why is the speed of light 3 times 10 to the 5th kilometers per second instead of 2 times 10 to the 5th?
Right.
That's not even a question in physics. And people used to say, well, the universe is made out of hydrogen and helium, because we didn't know about dark matter and dark energy, so it's made. And see, that's reflected in us, at least the hydrogen part, because our bodies are 3/4 water. The most numerous atoms in our body are hydrogen atoms, just like the universe. So you see, we reflect the universe.
Right.
And everybody goes, oh yes, that's very profound, very great. 30 years later, dark matter and dark energy make up 96% of the universe's matter and energy content. So now we go from being just like the universe to being kind of the very small minority. So humans, being the great rationalizing engines that we are, so now people say, well, of course, we have to be made of the kind of minority constituents because we are the part of the universe that is unique and can contemplate the rest of it, or sentient, right?
Right.
So it makes sense. So wait a second, dude, you just changed your story 180 degrees.
You moved the goalpost way beyond.
Yeah, it's like, come on. But that's what we do.
I see.
That's what we do.
I see. I'll ask a naive question. You have spent much more time than most peering into the interstellar medium, and people have spent thousands of years looking to the stars for meaning. So is it up there?
No, well, yes.
Welcome to the very first episode of Thought and Theory. Today, I sit down with Dr. Loris Magnani, a former advisor and professor of astrophysics at the University of Georgia. During his time as a radio astronomer, Dr. Magnani made contributions to the field that have made its way into curriculum I studied personally during my undergraduate as an astrophysics major. Should note before we begin, the first 40 or 45 minutes of this episode are a bit technical. However, you do not need a background in physics or astronomy to follow our conversation. If you're here for the more philosophical stuff, I recommend using the chapter markers below to skip ahead. However, if you're interested in physics astronomy, definitely stick around. You might learn something. Thanks, and please enjoy.
Dr. Loris Magnani, pleasure to have you.
Nice to be here, Will.
You are a retired radio astronomer.
That's right.
And you're credited with the discovery and mapping of over 100 interstellar hydrogen clouds.
Yes,
and
molecular hydrogen. Yeah.
They bear your name, too.
One of my, they're called the MBM clouds, and the first M, I guess, is my last name.
So before we get into the discovery of those MBM clouds, what is radio astronomy more generally?
So basically, as you know from physics, radio waves have very low energy. So typically they emanate from parts of the cosmos that are cold.
Okay.
Low energy environments. If you want to look at high energy stuff, you look at X-rays and gamma rays. Low energy stuff, you look at radio waves. There are exceptions, of course. Okay. But speaking broadly and generally, that's the case. So I study the cold interstellar medium, and the best way to do that is through radio astronomy. And that's I started doing that back in 1982, and it's been 43 years.
Yeah, goodness.
Wow.
So it's my understanding that the temperature range of these clouds are very low. I mean, we're talking like 10, 15 Kelvin?
Yeah, maybe up to 40 or 50.
Okay.
Molecular clouds, molecules are incredible coolants. They absorb energy to get their electrons or their rotation or vibrational modes excited, and then they spit out those photons as they de-excite, and that's energy that's being carried away from the cloud. And so that's cooling.
Right.
And so molecules are about the most efficient coolants out there. And so molecular clouds are going to be the coldest part of the interstellar medium.
So how is radio astronomy different from, typically when we think of looking through telescopes, go through the eyepiece and you're looking at something magnified, but that's not the case with radio astronomy?
No. For one thing, radio astronomy is done 24 hours a day. You don't have to wait till nighttime.
So no astronomer is out of a job during the daytime.
Right, exactly.
Okay.
We work just as hard at 2 p.m. as 2 a.m. So what happens is you can think of it, well, let's back up a step. Radio astronomy is really divided into two huge different streams, single dish and interferometry. Mm-hmm. Single dish is where you use one big telescope to look at the cosmos, and interferometry is use many telescopes to synthesize a larger dish.
So this would be a telescope array where you
An
have
array, that's right.
Okay.
And the type of astronomy that gets done in both is very different. If you want to look at bright point sources, you want to do interferometry. If you want to look at faint extended stuff, you want to do single dish.
Okay.
I'm a single dish radio astronomer. I don't know anything about arrays, or just very little. So basically, I look at faint extended stuff. So having gone in that path, you can do imaging. You point your single dish at one location, you get the intensity of radio signals from that location, and that's some level. You go to different points, you get different levels, and then you can make a map. Okay, or you can look at spectral lines, where you're actually, instead of looking at just the intensity at a given frequency, you're breaking up the signal as a function of frequency, and you can see individual emission and absorption lines.
And is this what helps
And
you?
that's mostly what I do.
Okay, so is that what helps you classify exactly what it is you're looking at? Is it provides a fingerprint for the emissions coming off of whatever you're looking at?
Yeah, basically we study the various molecules. Different molecules tell you different things about the density and temperature of the environment you're studying. And so by studying different molecules and different transitions within those molecules, we can get an understanding of the physical conditions of the cloud we're studying. And that's effectively what I've done for 4 decades.
Okay. So what are MBM clouds? I mean, they're interstellar hydrogen clouds, but are they different from ones?
Hydrogen, yeah.
Molecular
There's also
hydrogen.
atomic hydrogen clouds.
Okay.
So basically, let's back up a bit. In the 1970s, after the discovery of the CO molecule in space, of emission from the CO molecule in space, we started mapping the molecular emission from the galaxy. And that's because the most abundant molecule is obviously molecular hydrogen. But it's very hard to see molecular hydrogen from the ground for a multitude of reasons we don't need to get into. The second most abundant molecule in the universe is carbon monoxide. And so that's easy to see from the ground with radio technology, radio millimeter wave technology. And so in 1970, it was first detected, and throughout the 70s, they basically mapped the distribution of molecules in the galaxy. And they realized that just about all the molecular gases along the galactic plane. Okay.
That's understandable, I would imagine, from the collapse of
That's right. In fact, if you remember, molecular clouds are the sites of star formation.
Right.
Most star formation, just about all of it, is on the galactic plane, and so the two go hand in hand.
Yes.
Makes sense. So what happens was that about 1982, my advisor, who was Leo Blitz at that time at the University of Maryland. Sadly, he passed away a couple of years ago. We're all a certain age now.
Right.
And he had this idea that locally, if you look at our little neighborhood, again, think of the galactic disk is very flattened, right? So if I look towards the galactic center, I'll see this vast array of stuff, gas, dust, stars. If I look in the empty center, I see also a lot. But if I look directly above or directly below me, if I'm looking at a galactic distribution, it's something in the galaxy, I run out of galaxy quickly because the disk is very thin.
Right.
So these so-called, there's a coordinate system called galactic coordinates. And so if you look at high latitudes, galactic coordinates, which is basically looking directly above and directly below, if you're talking about galactic objects, you run out of galaxy quick.
Out of our galaxy.
I mean, that's where.
So that's into the intergalactic medium.
That's right. That's where you go look for other galaxies.
Right. Okay.
You look above and below, because if you look into the galactic plane, you see our stuff. You can't see it's hard. Right. It's hard to see the galaxies on the other side.
What's the angle range there that you can peer in intergalactic or interstellar medium?
So basically, once you need to get above 10 degrees latitude, 10 degrees off the plane, to basically start seeing a lot of stuff. 30 is better. Okay, so we did a survey. We looked for molecular gas at basically above 25 and below minus 25. So at opening angles like this,
right,
like that. And because at that time there were only, I think, like a half dozen little tiny molecular clouds. And so his idea was to look for more of these clouds to see if they were up there.
Mhm.
And that was my project. That was my project as a graduate student in the early 80s at the University of Maryland. And when I came up with a search catalog, the way that I kind of thought of regions where there might be gas was kind of a traditional old way. In the old days, in the 1960s, basically by looking at star maps, high level star maps that went down to 20th magnitude, basically. When you look along the galactic plane, if there is a molecular cloud along the way, because gas and dust are well mixed, if there's a lot of molecular gas, there's a lot of dust.
Okay,
That
so it was an
dust,
association of the
that's
material.
right. That's maybe the most important thing in the interstellar medium is understanding that gas and dust go hand in hand. More gas, more dust. Okay, so when you look along the galactic plane, if there's an interstellar cloud, a molecular cloud, because it's denser than atomic gas, if there's one here, okay, there's a lot of dust there. And so the stars behind it will be obscured.
Right.
So there'll be like a hole in the stellar distribution. Those are the so-called dark clouds. We can come back to that because dark clouds now mean something else because of an unfortunate thing. But in those days, dark clouds were basically places where the dust was so thick that you couldn't see stars behind them. And it turned out that all those guys were molecular clouds.
Gotcha.
So they did a catalog, Beverly Linds in the early 60s did a catalog of all these regions. There's more than 1,000, maybe even 2,000.
And I'm sorry, do these sort of things that block the stars, what wavelength do those block in? Is that an optical?
The optical.
So
That's right.
so you look out in there and you see just a hole.
Yeah, you take an optical picture of a chunk of sky, and if you see a place where the stellar distribution drops, well, it could be because of fluctuations in the stellar distribution, but if it really drops by a lot, it's because there's obscuring dust.
See.
And if there's a lot of obscuring dust, there's going to be molecules there. That was kind of the lesson from the 1970s.
Okay. And you guys know those emit in radio, though, so you could
Right.
observe them if you looked in radio.
Once you point your radio telescopes to these regions that are deficient in stars, all of a sudden you start picking up molecules.
See.
And again,
I'll hope to show a picture if I can find one that's not licensed of the clouds.
I think Barnard 68 is a classic example, something like that. And it's just like a hole. You see thousands of stars, and there's this dark hole that's chock full of molecules.
Got it.
The problem is that at high latitudes, the stellar distribution drops. So you got big jumps in just the natural, distribution of stars. You know that it's in small number statistics. Basically, if it's a random distribution, the uncertainty goes as a square root of the number of objects. Well, if the number of objects is smaller, you get a bigger fluctuation. So it's harder to see obscuring dust up there. At least it was in the 70s and 80s. Now it's trivial for reasons we can get into if you want. But back then it was hard. And so I basically looked at these beautiful 6x6 degree optical stellar maps of the sky, trying to look for regions of obscuration at high latitudes. Many of those were just natural fluctuations in the stellar density. But some turned out to have molecular gas, many more than we thought. When we went out to look for molecular gas in this search catalog that I had come up with, we were thinking that if we got 4 or 5 clouds out of hundreds of possible candidate positions, we'd be happy. We found nearly 200.
Wow.
And that was the genesis of the high latitude molecular clouds. So basically, there was more molecular gas up there than anybody had imagined.
I see.
And 57 of the couple hundred are above 30 degrees. They became known as the high latitude molecular clouds. And in the catalog, they're listed, 1 through 57, and they became the MBM clouds. That was my thesis, basically.
In terms of observing these, I read through a bit of the 1985 paper. And
wow. I admire you.
Well, there's a lot of tables and charts that
Right.
I'm like, I think I understand what's going on here.
Yep.
But I noted that you guys were using tracer molecules to identify.
Carbon monoxide. The 1-0 rotational transition of carbon monoxide.
Okay, so that's what you'd previously explained.
Yeah, because that's if you have a decent amount of molecular gas, like anything else in physics and astrophysics, anytime you make a statement, it has to be qualified by 8 million exceptions.
Yeah.
So I'm speaking broadly, but broadly speaking, if you have a lot of molecular gas, the best tracer is the 1-0 rotational transition of carbon monoxide at 115 gigahertz.
See.
Now, again, the cloud is mostly molecular hydrogen, but, it's very hard to see from the ground. You kind of need to have an infrared or an ultraviolet satellite to do that these days.
So this is going back a bit, but you mentioned that we have this blockage of the intergalactic medium because of the disk. So does this mean essentially from
Say interstellar.
no,
Okay.
I mean
I see what you mean. Yeah. Okay.
out
Yes.
into the. So
Yes.
do we have this region 30 degrees on either side, 40 degrees on either side, where we can't see the intergalactic medium?
In those days, there was something called the zone of avoidance, where basically, 30 is, there are reasons why we pick 30 as our criterion for high latitude. Let's bring it back to about 10 or 15. If you look into the galaxy 10 or 15 degrees above and below the galactic plane in either direction, in those days it was called the zone of avoidance because you couldn't see galaxies there. Okay. However, as time passed and basically receiver technology got better, you can see radio waves. Radio waves permeate the dust, and so you could begin in the late 80s and 90s. You could begin to see atomic hydrogen emission from galaxies that are beyond the galactic plane.
But in the direction of.
In the direction, yeah.
I see.
So the zone of avoidance. In other words, it was a big problem
Yeah.
in the 60s, 70s, and 80s. By the 90s, nobody cared because you
Gotcha.
could see through it with 21 centimeter atomic hydrogen emission.
I see. So that paper came out in 85. That was when you published your results.
A letter came out in 1984 because it's funny because one of the reasons why they didn't make a bigger splash, the discovery of these clouds didn't make a bigger splash, is that in 1983, the IRAS satellite, infrared astronomy satellite, went up and it made the first infrared survey of the whole sky. And basically, again, if you've got clouds with a lot of gas, they've got a lot of dust, and dust emits thermally in the infrared. And so we knew that they had found a bunch of stuff up there.
And that was sort of
that became known as the infrared cirrus. So we had to rush to publication. So they actually beat us by a couple of months. And so the infrared cirrus there's more of that than high latitude clouds. The high latitude clouds, molecular clouds, turned out to be the densest parts of the infrared cirrus. A lot of people assume that we found the high latitude clouds by looking at infrared maps, but it's in one of those great heartwarming tales of science. My advisor asked the leader of the infrared, one of the leaders of the infrared astronomy satellite project, if we could look at their preliminary maps. And the guy said, no.
Oh, he didn't want to share his data.
Right.
Is that data you would have used?
Yes, because in 1986, like I said, when we kind of matched the two data sets together, we realized that the densest parts of the cirrus were molecular. And so we would have found, found many more clouds that way, and it would have really helped. But, I mean, they had their reasons. They spent millions of dollars to get that satellite up, decades, at least one decade, if not two, of work to get all the instrumentation and everything going. And so they wanted to reap the benefits of their work.
Sure.
So it's understandable, but this happens all the time in science. We're not quite the big happy family that sometimes we're portrayed.
So how has the culture of academia changed since you were doing research in the 80s and 90s to now? Is that an attitude that still permeates?
Yeah, but less so because it's an excellent question you asked. The way research is done has changed in the sense that now people tend to work in much larger groups. Okay. I mean, the MBM clouds, Magnani, Blitz, and Mundy, that's 3 people. A lot of the original papers have those 3 authors on them. Okay. In those days, single author papers or papers with 2 or 3 authors were common.
Right.
Okay, if you look at the AppJ now, papers
Yeah.
have 5, 10, 200
It's et
authors.
al. And you click expand and it's
Exactly.
half the page.
So astronomy is done by large groups because they usually require to get the data, they require these days satellite work, which involves lots and lots of
Right.
people. And so what happens is, since you have such large groups, in one sense, you don't have you have less direct competitors because they're all in your group, basically. There might be, two big groups only.
I
So,
see.
so in that sense, it's not as people aren't as particular because everybody's working together. On the other hand, if there are two competing groups, they're not going to share data either. That's
Wow,
just the
that's
way it goes. I
interesting.
mean, before publication.
Oh, I see.
There
Okay.
are exceptions, okay, but by and large, people tend to be very um, proprietary, at least the first year or so, with their data.
Have you ever seen that hinder scientific progression?
Yes, like I said, I gave you an example. It
Right.
hindered us
Yeah.
tremendously,
Goodness.
but that's the way the game's set up. We
I
all
see.
want to have careers, and
Yeah, I guess so.
you
That's spent
know,
your whole life studying that.
it's yet another examples of why human beings are the wonderful species we are.
Right.
If I may interject, one of the funniest cartoons I ever saw was it was a New Yorker cartoon, and there's these two dogs that are dressed up in business suits at a bar, and they're having cocktails, and one of them is telling the other, "It's not enough that we succeed; cats must fail." And so that's the human species in a nutshell. It's not enough that we succeed; our competitors must fail.
Yeah. So has that had an effect on the competitiveness of the field in terms of entering the field, or has it always been a highly competitive
It
field to
was
be
always
in?
highly competitive. Now things are worse because of the funding decline.
I see.
And so at a time when interest in astronomy is maybe greater than it has ever been, and we have so many young people that are not just astronomy, physics too, but
Right.
astronomy is harder hit than physics for reasons that we can get into if you want. But so many people want to become astronomers, and there's less and less opportunity to do so. Departments are shrinking.
Right.
And as
Even
you can see
physics
from
department.
UGA,
Yeah.
just our own department,
Yeah.
when I joined it in 1991, there were 26 full-time faculty. I think there are 17 now,
Goodness.
and that's normal.
And how much of that, and this goes for the group data sharing as well, or not sharing, but having a large group working
Yeah.
on data. Does a lot of that come from the fact that now a lot of data is already out there? It just needs to be analyzed since we have
Yeah.
these all sky surveys.
Yeah. One of the things that astronomers have done more so than any other branch, well, maybe not the Human Genome Project, but uh, more so than physics anyway, is we set up huge projects that usually cost millions or tens of millions of dollars, sometimes more, to get these enormous databases. And then, they're calibrated and thrown out to the public, and then the public mine, M-I-N-E, they
Mhm.
mine such databases. So data mining is now a branch of astrophysics. I think the last decade of my career, I didn't take new data. I just mostly used data that was out
Right,
there.
right. So, I mean, does that open the door for people that are lower down in the astronomy ranks, graduate students to go in, or even undergraduates to go and search these data sets
Sure.
and
I mean,
find patterns?
in theory, yes. The problem is that often you need to really get something out of these databases, you need a lot of experience. So if I never, I'm hopelessly, like all old people, I'm hopelessly stuck in the past, and so what happens is I always preferred to take my own data because I knew what problems there might have been. Hey, the weather wasn't good that day, or the data's a little bit noisier because the receivers were acting up. When it's a big data set that you haven't taken yourself, you don't know those little details,
Yeah.
and so you're prone to making mistakes with it more so than you would if you took your own data. Having said that, it's one of those things that's just the way it is now. There's no going back. But I really do think astronomers should maybe take less of these enormous data sets and start thinking more about the data we got. There's too much data gathering and not enough
Yeah.
data thinking about.
That's interesting. We've spent all this money and time producing all of these wonderful instruments that collect loads of data, but now the field is so underfunded and so competitive that there's nobody to go and analyze this data.
That's sad but true.
Yeah. And do you have any idea, I don't know if this is something you've thought about, but the rise of AI able to analyze and sort through data very quickly?
So again, AI has to be trained.
Yeah.
Now, it can be trained successfully to find things that have escaped detection, but I I was kind of an expert in looking for weak signals, weak spectral signals in spectra. And I challenge any AI program to do better than I can
Right.
with the naked eye. But then again, I've literally looked at hundreds of thousands. I'm not exaggerating. I've looked at not tens of thousands, maybe not many hundreds of thousands, but I've looked at hundreds of thousands of spectra with the naked eye over the decades, and I can tell you if a signal is real or spurious or likely to be real. And I challenge anybody to come up with an AI program that'll do better than me.
Right.
Then
Understand.
again, if you don't look at hundreds of thousands of spectra, you haven't trained your brain
Right.
to do that.
Right.
So I'm a little bit of a skeptic for what AI in this version can do.
I see. Because you're reading minute details on incoming spectra.
Yeah, and again, you can say, look for adjacent channels where the signal is so much higher than the noise, and people have written spectra like that. But I've written programs like that. But when the programs that they've written um, certainly don't do better than somebody who's
Right.
highly trained can do. Now, AI, of course, takes those ideas and learns.
Right.
Okay. So maybe I'm being a dinosaur and not realizing that, hey, someday AI is going to find things that I couldn't find. For instance, AI has looked, I know that in Dr. Hall's group, they've used AI to find traces of planets in these dust
I
disks
see.
that they couldn't pull out by just looking at the dust data. So I'm not saying that it can't work. Of course it works. But I'm just saying that for what I do at the
I see.
moment, unless AI changes drastically in how it works, uh, I'll beat it every time.
I see. Yeah.
I'll bet money on it.
Huh? Well, it's a challenge. Somebody
Yeah.
make an AI beat Dr. Magnani. Sorry to interrupt, but if you're enjoying this video and could see yourself watching another one in the future, please consider subscribing. It really helps me gauge the level of interest these videos generate, as well as allowing me access to future potential guests. Thanks. Now back to Dr. Magnani. So I wanted to ask more on the competitiveness side of this. I'm going into my 4th year, and
You have my sympathy.
yeah, goodness, it's something. But I think there's 6 of us that
Yeah.
might graduate, 5 or 6,
Yes,
and
that
we
sounds,
started
yeah,
with
that's typical.
30. And so you've
That's
been an
very
advisor.
typical. Oh yeah, yeah.
So what does
That's
that
very typical.
progression look like as you've been an advisor, seeing students drop here and there? I mean, it's
Yeah, that's, dropping by 80% is normal. There's nothing,
goodness.
that's the way it is. It's hard. As you know, it's difficult. And it was difficult for me, by the way. I struggled mightily as an undergraduate.
Yes.
Okay, so fascinating but difficult. For a multitude of reasons, we lose a lot of students along the way, even very enthusiastic students. And these days, it's not the tragedy that it even was 30 years ago, because as I said, once you get out with your undergraduate degree, first of all, it's become very hard to get into graduate school.
Yes, it has.
And
In my
I
class,
find that, I can't explain that, by the way,
wow.
but it has. And once you finish graduate school, like because of the decline of the field as far as resources, funding,
Mhm.
it's hard to get a permanent job. So you work all through your 20s to master the discipline, or at least an area of the discipline. And then you have to go write computer programs for Walgreens or something.
Yeah.
You make a lot of money. Nobody with a PhD in astrophysics is going to be driving an Uber. Okay, you'll get a job, but you could have gotten that job with just a couple of years of computer science
Right.
training.
Yeah.
You didn't have to do 6 years of graduate work in some, obscure area of astrophysics. So it's sad. The profession has not met this challenge. We're kind of hiding our head, burying our head in the sand.
And
And
stars, maybe.
yeah, I know. Yeah, but it saddens me. It saddens me because it is clear that your generation will not have the opportunity that I had, and that's just 40 years ago.
Yeah.
And that saddens me because I had so much joy and satisfaction doing this that I like other people who want to do it to have the same opportunity, but it just isn't so, at least
See.
not in the U.S.
I've certainly noticed, at least going in my 3 years of undergraduate here, seeing students come in very enthusiastic and almost have their enthusiasm beat out of them, ironically, by having to do the actual physics itself. It's like they come in so
You mean the
excited.
classwork or?
Yeah, the classwork.
Yeah, well,
It just,
it's always been hard.
yeah. So, I mean, that's probably the initial
You
strain, and then you have to get a job.
you know, the progression is you take introductory physics courses in your first 2 years, then you take higher level courses your third and fourth year, then you go to graduate school and it's the same discipline. You take more mechanics, more E&M, more quantum mechanics at a higher level. Okay, I didn't really learn the stuff till I started teaching it.
Wow, is that common, do you think?
Well, I'm a little slower probably than most, but people usually get it in graduate school. But the best way to
Okay.
understand something is to actually teach it.
Right, yeah.
So, I know E&M now. I'm confident that I can go back as an undergraduate and get at least a B in those courses.
I got a B in the first EMAG course, so we'll see if I take the second one. But
If you want to go to graduate school, you have to.
right, I'm still not sure about graduate school for physics
I
or
understand.
astrophysics,
I
but for
understand.
reasons we've discussed, right? The
Yeah,
field
no,
is slim.
I can't blame you. I wish I could say something positive.
Right, I understand. You actually, I hate to be on the downer note again, but you
Oh, I'm Mr.
mentioned
Downer, in case I'm a pessimist by nature. So
we in conversations during your time as my advisor, you had mentioned that you were even miserable during undergraduate at times, where it's
I
just
was.
slugging through the
I
coursework
was.
and
I had a tough. I mean, I went to an Ivy League school for undergrad, and the basic difference between the students at an Ivy League school and UGA, a large public university, is not that the students are so much better than here. The best students at UGA are as good as the best students
that's interesting.
at Columbia or where I went, for instance. It's just that everybody was good in the class. Here, there's the good students, the so-so students, and then there's a whole
Oh, I see.
cadre.
So the whole class was on par with the best students
Yeah,
that you would find at.
that's right.
I see.
That's
Okay.
the only difference. It's not, you see, the best is, pretty much the same.
Right.
It's just that at those places, everybody's
Well, that
good.
sounds amazing because you go to university and you get a lab partner who doesn't do anything, but that doesn't happen over there. So
No.
so you get, and I've noticed at least in
I
my
was a
time.
mediocre student at Columbia.
Well, that's where you want to be then, right? Because you're surrounded by people who are
Well,
pushing you forward.
in theory, yes, but when you're actually thrown into that meat grinder, it was very ego deflating to.
I see.
I've told this story many times, and it's worth repeating. So, um, there was an exam in senior year, I think. I think it was quantum mechanics, okay, 4,000 level quantum mechanics. Now, another difference at a place like Columbia back then, I don't know what it's like now, was that the senior level classes, you could have graduate students. There were 4,000, 6,000
Yes.
levels, just like us.
Yes.
But in our classes, it's mostly undergraduates in those classes, with only 1 or 2, 3 graduate students at most. Columbia was the other way around. It was 3/4 graduate students, 1/4 undergraduates.
Intimidating.
Exactly. So in one of those classes, quantum mechanics, I take this exam and I just don't know how to do anything. It's just all the questions. I don't know how to do these questions. So I, did my best. We get the exam back. We used to take the exams in these little blue booklets
Yeah.
back then. And I look at my exam booklet and there's not a mark on it. And I'm thinking, oh my God, what happened here? Did the professor think I was cheating and, refused to
Yeah.
mark it? It's like, I looked at it more carefully, and on the inside front cover of the blue booklet, there was a -80. So basically, the professor, what was his, it'll come to me later.
Sure,
He
sure.
was a great professor,
Yeah.
Professor Baker, I
Baker.
think. Don't quote me on that.
Okay.
I'd have to.
I'll go digging and look
Yeah.
for it.
He's passed away too, sadly.
Right.
Anyway, he he had seen that I didn't know how to do anything, gave me 20 points for showing up and being a good sport, and that was it.
Yeah.
Okay. On that very same exam, where I got a 20 out of 100 because I didn't know how to do anything, one of the graduate students in that course got a 96. Okay. What is funny is that he got everything right. However, he solved one of the problems not very elegantly. So the professor took out 4 points for lack of elegance. In other words, he got the
That was
problem
what's
right.
written on the
So
exam. Lack of
he lost
elegance.
style points.
Oh my goodness.
Okay, in an exam where I, got 20, a guy gets everything right, loses 4 points for lack of elegance.
Oh man.
That's the kind of competition we were up against.
And I've never even seen something like I feel like that doesn't happen often now in academics, because I might get a +1 point if I draw a cat on my quantum exam.
Yes.
Dr. Wiegard's exam page was full of cats.
I didn't draw enough cats, I guess. But the point is, I struggled mightily. My last year, my senior year, I got a C- in ENM2.
Does that give you the credit?
Yeah, in those days, yes.
Okay. It doesn't now.
I understand.
Yeah. Yeah, they moved the cutoff from D to somewhere in the C range.
We changed the rules to make it a little bit harder. Yeah. But the point is that when I left undergrad, I really didn't understand physics. I'd been exposed to it. I muddled through. Now, when I went to the University of Maryland for graduate school, I all of a sudden became an average student. Being below average at Columbia, I was just so I did okay in my coursework at Maryland.
Was that because of a maturation in your academic, or a selection process from the graduate?
Selection process.
Okay.
The competition wasn't as fierce.
I see. So we can bring this to a lighter note, because so far it's been, undergraduate's miserable and this is the hardest subject you can study. You did...
math is actually harder.
Yes. Yeah, it's definitely... The mathematicians in our quantum classes don't get below a 95. It's unbelievable. Yeah. I have a quote from you. It's not a direct quote, but regarding... I was in your office when you're my advisor, struggling through, goodness, what was I in? I think I was in those intro modern physics course. And I was like, I don't know if I can do this. This is really difficult. And you said something along the lines of, it's not a question of can you do it? You can. It's just whether you want to, whether you want to make those sacrifices.
That's right. Yeah. I mean, if you have a given basic intelligence, and all our majors do, if you want to, you can get through it at this level. You might not be a great physicist. You might not ever do fundamental work in the field, okay? But you can master it at the 4,000 level. Some people, like me, have had to pour in an enormous amount of time. And then the question becomes, is it worth it for your life to do that? Because you can argue, I can argue, that it can sort of ruin your life. It almost did mine. I mean, I was so stubborn. I can tell you another anecdote. One of the reasons why I saw it through. Another difference between Columbia and UGA is when I was at Columbia, we had 3 Nobel Prize winners on the faculty. And there was a fourth one who everybody said should have won the Nobel Prize, but she didn't get it because she was a woman.
Oh, goodness.
Okay.
In the 80s.
In the late 70s. This was the late 70s. So the faculty are all these names,
right?
And basically, I had a class with one of the Nobel Prize winners, and he just used to spend it was a one-on-one lab class. So you basically did a lab, it was senior level.
One-on-one with the instructor.
Yeah, you did a lab, and then you sat down in his office, and he went over the lab with you and asked you questions. Very Socratic.
Yeah.
Okay, and it was humiliating. Not just me. He did this to everybody, but he insulted you.
Oh, goodness.
He effectively implied that I was stupid. I'll tell you, just again, the sort of stuff that could happen then that cannot happen now.
Right. Yeah.
Okay. So.
Sorry, this was your undergraduate.
This is undergrad.
Wow.
Yeah.
Maybe I could see that in grad school if you have an advisor who's really but in undergrad.
It gets better. It gets better in grad school. But anyway, I'm trying to explain what I did, and he's asking me questions, and I'm just stumbling and just And at one point, now remember, I'm in his office. Mm-hmm. Okay, I'm sitting down across from his desk. He slams his hands on the table, gets up, and walks out of
his own office. Where's he going?
So I'm standing there. I got my little lab in my hands. He's gone, and I'm wondering, what do I do? He hasn't graded it. because he's been
You've
yelling
got
at
his
me.
red pen right
He's
there,
been
right?
yelling at me the whole time. So I waited 10 minutes and then I left. What did I
Did
do?
that end up being graded?
I don't know. I passed the course, so
Wow. And that was the Nobel laureate.
that's the Nobel laureate.
Goodness. Wow.
So the point is that I forgot how we started this, but I got chewed out basically and made to feel like I didn't understand anything.
Right.
We don't do that these days.
Yeah, it's very, that's one thing I have noticed. Yes, it's extremely difficult, but there's a lot of positive reinforcement as you go through.
Yeah. Part of it is culture has changed, and part of it is that way. He might have had good intentions, toughening us up, weeding us out, whatever you want to say. But it was just so anyway. Oh, I remember now how we started this. So my response in those days, by being, he also told me once explicitly that I'd never be a physicist.
Goodness.
Yeah.
He's just trying to get you out. Goodness.
Well, it didn't
You're an
work
astronomer.
because it didn't. Yeah, A, I'm an astronomer.
Yeah.
B, that just said that's it. I'm doing this.
Yeah.
Maybe
Maybe that was a drive that he had as an undergraduate or graduate student.
It could be. It could be. These days, it's probably counterproductive because again, culture has changed. But in those days, it just made me mad, and I said, But that's it. Remember, I was very like all young people. Well, let's not make. I was very immature in those days, and so I reacted. Well, you can argue negatively or positively. I said I was going to get my degree now, all the way through. I was going to go to grad school. I was going to get my PhD to quote unquote show him, and I did. So I even made a career out of it.
Yeah, quite a successful one.
yeah,
I mean,
yeah.
we've got MBM clouds now.
But as you mature, you realize that you should never do things to prove something to others for the simple reason that they don't care.
Right.
In other words, if I had gone back and said, "Look, see, you said I never did," he wouldn't care.
You did all that for me?
Yeah, he could have cared less.
So what would you say? You've mentioned one of them, just straight determination. But what are the other criteria for success in more broadly the STEM fields?
You need to have a little bit of quantitative ability, but again, all our majors do.
Right.
You have that. So let's leave that aside. In other words, I can't take somebody off the street and teach them 4,000 level E&M. Okay, I mean, you have to have some quantitative predisposition, but by the time you're taking the 3,000 and 4,000 level physics courses, you sort of have that.
Right. You've got the mathematical foundation.
The ones that really were lost stopped at the 1,000 level. They got a D and they stopped there.
Right.
Okay. So assuming that you have that, you definitely need determination. And the other thing is you need time. I don't think you can work a 20, 30-hour week. Some people have to. I understand that. That's the sad part.
Yeah.
Some people have to support themselves. And so they work these. That's not enough time unless you don't sleep at night.
It's quite a barrier for a 4-year degree.
So it's hard, but it's always been hard. And every class has got that 1, 2, or 3 students who get it and somehow you know what I'm talking about.
Absolutely. Don't take notes. Just
but the interesting thing is that classroom performance and research are totally disconnected. I was mediocre in the classroom, but I turned out I was a pretty good researcher.
Yeah. So I have a couple quick questions. Well, not quick.
I'm here for you, Will.
No, yeah. What is it about the astro prefix that's so sensationalized? I mean, people have seemed to take this word astro, and if you put it in front of anything, it just means you're like some sort of genius. What's going on there?
Yeah, that cracks me up because, it's the physicists who really kind of understand the stuff, and God forbid the mathematicians blow us all away.
Right, that's the ranking. Yeah, math, physics, astrophysics.
Yeah. But the astrophysics has certainly a certain cachet to it for sure, absolutely. And I think I find the show annoying, the famous show, The Big Bang Theory.
Yeah.
But there was
little nerdy guy. Yeah.
We can come back to that if you like.
Sure.
I never considered myself a nerd, and some of my buddies in
I'm not
graduate
even sure what
school.
that means. I mean, and I'm not just being pedantic. I really don't know what that means. I mean, I know, of course, glasses and maybe like bad
bookish,
skin, but
yeah, basically, we don't need to get into the whole thing about that. But there
Sure.
was this hilarious line where somebody, one of the characters is named Sheldon, and he's this, super genius in physics. And anyway, he's very eccentric also. But at one point, somebody compares him to a rocket scientist, and he's insulted because a rocket scientist? I'm a theoretical physicist. So astrophysics has that kind of cachet. I'm not a rocket scientist. I'm an astrophysicist.
That's for the engineers.
Yeah, exactly.
I always thought that dynamic was interesting of especially in the physics field of we're so much better than the engineers. And I'm like, they're the ones that are doing all of the like important groundwork.
Yes,
And
we couldn't do a lot of this stuff
yeah,
without.
it's like, who built your telescope?
On the other hand, there is a mentality approach that is different. And there are sad jokes about it, but we're trained to do different things. All right. The job of a physicist, and even more so an astrophysicist, is to take a complex situation, throw out all the distracting parts, distill it to something straightforward, simple, that can be analyzed, and make predictions or solve whatever the issue is. An engineer is more goal oriented, in the sense that, I mean, they're both goal oriented, but the engineer basically has to make that pen work better.
Right.
Okay. And he doesn't need to distill it to its basics. Sometimes you have to make it more complex.
Right. So
Right?
so one
so
is
there are different disciplines, different mindsets.
sorry. One is exploring the pathway towards the end result, and that might be the physicist who
Right.
doesn't know what they'll find, but has to go through a process to figure it
Right.
out. And the engineer has this thing in mind that they want to accomplish, and they have to get to that end goal.
Right. That's right.
I see.
They don't to be charitable to them. They don't have the luxury of
I
exploring side paths.
see.
They've got to get this pen working by this afternoon. That's,
Yeah.
And so if they discover something interesting along the way, well, it'll have to be for another time, because that has to be done now. So yeah, we need the engineers, but that kind of focused mentality often doesn't help the physicist.
Yeah. Yeah.
We have a gift, the gift to be allowed to explore, and kind of go down dead ends. A lot of times we're chasing something down a dead end, and we have to back up and try something else.
A lot of people would say that of string theory, about where they've been a 40-year.
Does anybody believe in string theory anymore, except
don't
for
know.
string theorists?
I really don't know. I guess I'm not in the community enough to know.
Yeah, the problem is that all those guys are basically brilliant. I mean, the top people in that field are brilliant. So for me to sit here and say, well, string theory is clearly wrong, if Edward Witten was across the table from me, he would ridicule
Right.
anything I had to say about it. So the point is, it's hard to argue. But on the other hand, if you want to take an engineering mindset, what have they done recently? Like recently in the last half century, told us that there are 4 large-scale dimensions. I mean, duh. As somebody once said, that needed inventing.
Yeah. Oh, they've determined that gravity exists.
Oh, thank you
So-
again. Thank you.
Right.
Yeah,
Right.
yeah.
Another question: will Betelgeuse go supernova soon?
yeah.
Is that happening?
Well, soon in cosmic terms,
Well-
maybe not soon in human terms.
Yeah.
But yeah. And then sometimes between next weekend and 10,000 years from now, yeah,
That'd be quite something to see.
it would.
All of my fellow undergraduate astronomy majors, when we do our observations, go out and
You're always looking at.
yeah, it's like tonight, please.
Now, you have noticed, if you do that, you notice Betelgeuse is variable.
Oh yeah,
Sometimes
its brightness
it's-
really fluctuates.
I've seen it subjectively. I've seen it look brighter than Rigel, which is, but only once or twice. Usually, it's clearly dimmer than Rigel. So it is a variable star, and sometimes it'll surprise you with its little, bursts of brightness.
Right. And is that a common thing to see towards the end of a star's lifetime, or it's very
I
variable?
think so. I'm not an expert in stellar evolution, but I think once they're up there in the giant or supergiant branch,
Yeah.
of fluctuations on short time scales very short timescales by stellar standards are commonplace.
I think I asked that because I just finished stellar astrophysics. So the asymptotic giant branch, I could still draw it for you. It's fresh in my memory.
Cool.
So okay,
Very cool.
well, I'd like to switch gears here a little bit. What in your estimation, and this is a question about how this viewpoint of yours has changed as you've gone through academia, but what is the role of science? Like, what's the goal of the scientific enterprise? Easy question, huh?
Yeah. This is the sort of question where if you asked me to write an essay on it, I'd ask for a week, and then I'd ask to revise it a month later.
Right.
Okay, so
Right.
so in other words, I'll tell you something now, but if I change my mind next week, next month, next year, that's part of the game.
Right.
So in my opinion, the scientific enterprise, at least physical sciences, because I have to distinguish between physical and biological sciences, because basically the approach is totally different.
Yeah.
One is a reductionist science, the other one is more concerned with emergent phenomena, and that's two different ways of looking at nature radically. I mean, I don't know how you reconcile them actually. So let's talking about reductionist sciences like physics, astrophysics. Basically, our role is to make models to understand phenomena, natural phenomena. And the weird thing, I'm not the first person to comment on this, and I won't be as erudite as some of the people have said this, but basically the weird thing is that somehow we can understand a lot about what's going on with incomplete models or models that aren't really correct. I mean, why would that work? And yet it does.
So we're getting at something fundamental there. Like and I want to ask, and this is another giant question that I'll throw at you that's probably worth another month of thinking. But what is the role of truth in that? Because it seems that we build these models.
We don't need it.
So it's is it an approximation of truth? Are we building towards something?
We would like to think that it's an approximation of truth. That in other words, I can make a model of the atom that is really nothing like the quote unquote real atom, and learn a lot about how atoms work and how they interact with their environment and even predict things. Okay. So I have some confidence that my model resembles reality. But the fact of the matter is that at the end of the day, these models may be way off.
Right.
I mean, well, you don't have to look very far. I mean, I sat in on a course with you in general relativity just recently, which was a lot of fun.
Yeah.
And that enormous branch of physics is irreconcilable with quantum mechanics at the moment.
Yeah.
So those two models of nature, both highly successful, both highly predictive, are incompatible. So, logically, in my opinion, you only have three options. General relativity, that approach is correct. The quantum mechanics approach is wrong, and you need to make quantum mechanics like relativity. Or quantum mechanics is the correct approach, and you have to make relativity more like quantum mechanics. Or the third option is neither is the right approach, and you need a totally different approach. That was sort of what string theory was, an attempt
absolutely
in that direction.
Is there a possible fourth option that the universe doesn't owe it to us to make sense?
Well, that's a given. Because one of the things about studying astrophysics or at any level is that if you think about what you're doing, it's clear the universe wasn't built for us. So, I personally don't think there was a creator, but I could be wrong on that. But if the creator did this, he didn't make the universe for us.
I see.
It's just about all of it is totally inhospitable to us.
Yeah, right.
If you think about the density and temperature ranges we require to live, such a ridiculously, absurdly tiny fraction of the universe that it's like, really, what's the other 99.99999% for?
Yeah, actually, every part of the universe but this one planet.
Exactly, this is what I mean. It's absurd. Right. It's absurd. And so, what was the question?
Oh, well, I wanted to ask. We asked about the role of truth.
Yeah. Okay. So I think that our business We may have higher aspirations, which is fine, but our business is not truth with a capital T, as I used to call it. That's for other disciplines. You can have metaphysics, theology,
Yeah.
even philosophy. But for us, we make models that approximate nature and let us understand more about the phenomena out there and try to give us some predictive power, so that we can understand more about what's going on. Whether those models have any real, whatever that means, any real connection to nature is not our business.
See.
I mean, ideally it is, right? We would like that to be the case, but we can have tremendous success. We can build an H-bomb, okay, without really getting the physics right in a truth sense.
You see. So,
And I don't know, and by the way, and the point I was trying to make before is I don't know why that works. You could imagine a universe where if you didn't get the thing right, nothing would work.
right.
And then we'd be out of luck. Then we couldn't build an H-bomb.
One of my professors told me that in physics, we sometimes make the mistake of asking why, when really we should be asking how.
Correct.
So I imagine this is a broader science perspective where we're categorizing things, we're explaining processes, we're not explaining origins or why it's this way and not another way. I mean, we can't
Right. That's
examine something enough to tell you about why it's this way and not
right.
another
Yeah,
way.
why is the speed of light 3 times 10 to the 5th kilometers per second instead of 2 times 10 to the 5th?
Right.
That's not even a question in physics.
So and I want to ask about your experience with this too. I personally started in physics because I was, well, naively looking for truth. And I've come to this realization and pivoted more towards, metaphysics and philosophy. But do people make this mistake? Did you make this mistake of thinking that scientific enterprise could provide you with truth?
Oh, yes. I mean,
It's
when
very
you're young,
alluring.
when you're young, you're idealistic.
Right.
You're allowed. I mean, it'd be a tragedy if you weren't idealistic when you were young.
It's true, yeah.
But as you get older and cynical, and you realize, somehow it works anyway. What the hell?
So this is one of my pursuits. The 19th century, we saw the bifurcation of the field of philosophy and science. I mean, physics used to be natural
philosophy.
natural philosophy. Now the philosophy building is on that side of campus, and metaphysics is studied over there,
Right.
and we study physics and astrophysics in this small underfunded
And
building.
rightfully so, I would add. Yeah.
Okay, so that's what I wanted to ask. Do you see that bifurcation? I mean, it allowed both the fields to progress in different directions, but is there some rekindling, some knitting we can do back in those fields, or is that worth doing?
I think ultimately because we have different goals, well, I mean, I'm assuming, I'm projecting what I think they do. I don't really know what philosophers do. I'm not a philosopher.
Well, see, I might say
But-
that you are, since you are a scientist.
Okay. Well, my subjective view of what they do, my personal opinion of what they do, is that they're more interested with truth with a capital T. We realized somewhere along the way we didn't need it, and so we decided to go for it. That would not be satisfactory for them. The one thing that I wish they would do that is, in a sense, kind of more similar to what we do is I think a lot of their papers and at least the writings in the 20th century are needlessly obscure.
Right.
In other words, one of the things you learn when you write a paper in physics or astrophysics is you strive to make it absolutely clear, to make your meaning absolutely clear. Okay. I've read Heidegger, I won't say dozens of times, several times. I have no idea what he's talking about. Okay. It's like, really, dude, you can't express your thoughts in a way that is clear and concise. Now, maybe once you read enough of that stuff, that manner of writing becomes transparent.
So,
But I think at the moment, a lot of certainly modern philosophical writing is needlessly obscure.
so you wish they could cut through the fluff and have.
I wish they could express their thoughts more clearly. And let's put it this way, maybe for them, the thoughts are probably expressed in a clear fashion, but if they want us to read their work, See, I would in other words, if when I write one of my papers, if you have the physics background, you should be able to understand what I meant, because I've spent endless hours trying to make it clear what I'm saying. I don't get that with them.
Yeah.
Like I said, I'm a fairly intelligent guy. I score really well, and I scored really well on the English part of the SAT and the GRE. I mean, like really well. I read some of that stuff. I have no idea what that sentence meant.
Yeah.
Is
So
that my fault or is that your fault?
there's a loss of formalization in that whole branch. I mean, this is something that science benefits from so much, and this is for the whole STEM field broadly. Well, I should restrict my statement to the mathematical sciences, because we have this rigorous formal definition for everything. Everybody's speaking the same language. When I go and read Nietzsche, and then I go and read some other philosopher, Jung, I might, okay, these people aren't even speaking. Well, it's literally sometimes they're not speaking the same language. But in terms of ideas,
Well, I mean, Nietzsche is my personal favorite, so I do like his colorful
I see.
way of expressing. In other words, I'm allowing him some artistic
Right.
leeway that I wouldn't allow some of the
I
20th
think he
century
gives
guys.
this. I'm reading Beyond Good and Evil right now, just
Oh yeah,
sort of going
great
through
book.
it. He gives that same criticism you just gave to all of the other philosophers.
Excellent. I knew I liked him for a reason.
So I do have to ask.
Sure.
You had mentioned at one point that you don't think that there's a creator, and it doesn't
Right.
seem obvious to you that that would be the case.
So the problem of creation is absolutely fundamental, and it's an ancient idea. And so again, I'm not a philosopher. At best, I'm an amateur, but I've read a bit here and there over the decades, and so here's my distilling of it. So you go back to the pre-Socratics, okay? So Parmenides, this guy called Parmenides, basically said that nothing ever changes.
Yeah,
Everything is as it always was and
I think this
always
was
will be.
Zeno's philosophy as well.
Could be, but Parmenides came first. So I think, I could be wrong on that. So anyway, Parmenides says that nothing changes, and you can say, well, that's stupid. I mean, today's sunny, tomorrow's raining. That's a change. He says that's superficial and meaningless. Nothing at a fundamental level ever changes. Always like that, going an infinite way in the past. It'll always be the same, an infinite way in the future. Counter to that, so that's kind of a continuum that never changes. Counter that with Heraclitus, who basically said everything's changing all the time. He's the guy who famously said you can't step in the same stream twice,
Right.
because the water
It's a
is
different
no longer,
stream
it's a
now.
different stream, it's
Yeah.
different water. Okay, so there, in other words, creation is continuous there. In one, there's no creation because it was always the same, always will be the same, no creation. The other one is continuous creation. The two are separate poles. So there is no way to, yin and yang, whatever you want to call it, there's no way to marry them. They're two totally different conceptions. So the reason I went into that tangent is when you ask me about creation, while I don't believe there's a creator, however, there could be, because I can't explain a universe that comes out of nothingness.
Mm-hmm.
And I understand that the Big Bang, we can only go back to the Planck time, but that's a cop-out.
Yeah.
Everybody's more interested in finding out what happened at time t = 0 or before. Okay? So let's say that to deal with that, you need a creator. I'm even willing to concede that, because again, the act of creation is irreconcilable with an infinite past and an infinite future. So you got to sort of stick it in there. So if you need to stick in a creator to make the universe, quote unquote, go, I'll grant that.
So you can grant that as a matter of definition.
As a matter of as almost necessity more than.
Right.
Okay?
I think that is the argument that Parmenides, or that springs from Parmenides' theory of nothing changing, is that, well, things change in the sense that they might be in, like, this water bottle might be in a different place as it was before, but it had to have the potential to do that, and then something had to move it. And you can go through an infinite regression and say, well, there had to be something.
That's the prime mover, right?
Right, the unmoved mover. But
Right.
that's not a description of God. That's That's a definition.
Right.
Something
And
to be
I'm
at the
willing to grant that that might be, if you want to stick that in there in your logical system, I won't argue. But to go from that type of creator to one that cares whether I cheated on my wife or my income taxes,
right.
and will doom me to an eternity of damnation, or nah, that's ridiculous. I don't believe that that's the way to go. It
See,
doesn't work for me. It makes no sense for me. Since we like a little bit of amateur philosophy, in that respect, I side with Bakunin, the famous Russian anarchist, who perhaps jokingly said that if God existed, we would have to abolish him, because a God that would be so capricious, sort of toying with our lives in that matter, needs to be overthrown.
you see.
So in other words, I'll grant you the definition of a creator because I don't know how to make something out of nothing.
Sure.
All right, but to go from that to a personal creator who's interested in what I do that makes no sense to me. Having said that, so that we don't offend anybody, and because I don't want to offend anybody,
Sure.
my mother raised me not to offend people.
Right.
Okay, so I would never ever argue my point of view with a believer for two reasons. One is, who am I to tell you what you should think? And secondly, life, I think, is hard enough for everybody, regardless of what you believe or you don't believe, that if you feel you need that to get through life, I don't want to take that away from you.
Yeah.
I have my own ways of making sense of, life and death. But I realized a long time ago, perhaps too late in life, but I realized a long time ago that my understanding of my role in the universe, even if I explain it to you, it might not help you. In other words, it's not only am I not going to be able to convert you, it might not even help you at all. It might make things worse, and I
Right.
certainly don't want to do
Right.
that.
So I have to ask, all of the ideas you've just laid out, how much of that has been influenced by your study of physics and astronomy? And is this
Tremendously.
okay? Because I've experienced the same thing, where you go into the field and all of a sudden there's like this model and you think it's truth, and you're like, well, what is truth? And you go through. What did that process look like for you from the time of being pre-undergraduate, undergraduate, studying as a graduate student until now?
Well, I mean, it evolved, right? It has to evolve because I know so much more. I mean, I was at UGA from 1991 till last year, and sometimes when I think of how I taught those first classes, the first few years, it's like I almost want to go back and refund those poor kids' money, because I could do a much more sophisticated job now, but it took years to kind of crystallize these ideas. Um, so so yeah, I mean, uh, the more you learn about the universe, I do think and this is true regardless of whether you believe in a personal God or not. Okay. I do think that what Steven Weinberg, the Nobel laureate, who did fundamental work in, basically field theory, what he said is that the more that you study the universe, the more pointless it seems. The more that you study physics in the universe, the more pointless everything seems. And so yeah, physics has really forced me into that. I mean, I was religious when I was a kid. I was raised Catholic, and I probably, kind of had some sort of faith till my early 20s. But then the more I studied, I had to give it up. That's not true for everybody. Okay, right. Some people can reconcile their faith in a personal God or and that's been good for them. I can't do it.
Right.
That's all I'm saying is I can't do it. I was religious. I lost it, and I'm okay without it.
I see. So that the theological perspective, that's a huge source of meaning for a lot of people.
I know. That's the reason why I don't want to argue with anybody about it.
I see.
I came to a personal understanding of what I gave meaning to my life, even though I believe that once I die, it'll be oblivion. It'll be nothingness. Okay? It's hard to kind of make sense of things when that's what you believe.
Yeah.
Theology, a religion, especially a Judeo-Christian religion, basically kind of takes care of that because there's an afterlife,
Mhm.
good or ill. There's an afterlife. Okay. So if nothing else, the can gets kicked down the road. And so, okay, maybe they're right. And I can't make that work for me. But if it works for them, why would I take that away from them and make them face what I think is the most devastating existential question there is, oblivion. Why
Yeah,
would I want to,
it's
it's like,
definitionally existential.
yeah, why would I want to do that to somebody?
Right. For that meaning, you mentioned you've been able
Yeah.
to construct that in your life absent from a religious structure. I'll ask a naive question. You have spent much more time than most peering into the interstellar medium, and people have spent thousands of years looking to the stars for
Right.
meaning. So, is it up there?
No, well, yes and no. I mean, like I said, I was inspired by physics to come up with a modus operandi with how to, live my life and remain sane. But no, I don't think there's any. Like I said, it's almost like so. Here's how what's interesting about human beings that is related to this. I always go off on tangents, but I try to come
No, it's good.
back.
It's good.
Okay, so when I was young and learning physics and cosmology, people at that time we didn't know about dark matter and dark energy. Okay, so the baryonic content of the universe was thought to be all there is. So as you know, that's only like, 4%
Yeah,
of the
it's
closure
small.
density. So
Yeah,
the universe expands forever, gets colder, blah, 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 and that's it. And people used to say, well, um, sure, the universe is made out of hydrogen and helium because we didn't know about dark matter and dark energy. So it's made, and see, that's reflected in us, at least the hydrogen part, because, our bodies are three-quarters water. Okay,
yeah,
and water, as we know, is H2O. So you see the most numerous molecule, the most numerous atom, if you want to break it down to atoms, the most numerous atoms in our body are hydrogen atoms, just like the universe. So you see, we reflect the universe.
right.
And everybody goes, "Oh yes, that's very profound, very great." Uh, you know, 30 years later, dark matter and dark energy make up 96% of the universe's matter and energy content. So now we go from being just like the universe to being kind of the very small minority
Yeah,
constituent
I've
of the
never
universe.
considered that from a constituent's point of
So
view.
humans, being the great rationalizing engines that we are, so now people say, well, of course, we have to be made of the kind of minority constituents because we are the part of the universe that is unique and can contemplate the rest of it or sentient, right?
Right.
So it makes sense. So wait a second, dude, you just changed your story
Yeah.
180
You moved
degrees
the
and
goalpost
you
way
move. Yeah,
beyond.
yeah. It's like, come on. But that's what we do.
I see.
That's what we do.
I
So
see. So, and on meaning found in the stars, an idea that I always thought was funny is ancient cultures, Aztecs,
right.
particularly the Egyptians, they saw the sun as God or as a
Sure.
god. And
Sure.
if you go outside and look at it, it kind of makes sense. It's this
You can't
giant
stare
orb in the
at it, right?
sky.
It'll blind you
I
if you
can't
stare
even
at it.
look at it.
Right. It's
Like
so
there's
bright,
brings me all of my light for my crops, and
Right.
sometimes the moon comes along
Hey,
and it goes out.
hey, you're making a strong case.
Right. I mean, I understand that conception of God. And
Right.
earlier we had talked about, well, we can do science in the absence of truth, but we would hope we could be
Of ultimate
naively,
truth.
right, with a
Yeah.
capital T.
With a capital
We
T.
can be naively hopeful that that's what it's aiming towards. But
Yeah, you'd like that to be the case.
have you been able to do that with constructing meaning outside of either science or religion to see, is there something fundamental here that I'm pointing towards that I can hope towards?
No, so I can't. Okay, again, that's not to say other people can't do it. I can't do it. So what I decided to do is sort of turn that argument on its head, and say that the meaning in my life will be that I will struggle against. I define my life and its meaning in struggling against this horrible cosmic joke of where I'm alive and sentient for hopefully 80 years, or maybe even a few more, but hopefully 80 years. I mean, 80 years divided by, 13.4 billion is zero.
Yeah. Yeah.
So I will have been around for basically, effectively zero of the universe's existence. That to me seems and there will be no afterlife, so I won't whatever awareness I have now will be gone. There'll be nothing. And to me that seems like a cruel cosmic joke. So rather than so the way I make meaning out of my life is that despite that, horrible curse, I will be defiant and live what I would like to be. What I would like to be, it hasn't always been. What I would like to be a moral, ethical life, despite in when it's in fact meaningless.
Right.
In other words, uh, I will make this futile gesture. One way of putting it that might make more sense is any idiot can fight if they think they can win. But to fight when you know you must lose, that I say is true courage.
So there's a nobility.
There's a nobility. That's how I've decided to make sense out of it all. The nobility will be in fighting against this horrible cosmic cruel joke, despite the fact that there is no victory. There is actually nothingness, but I nevertheless will try to be hopeful and be a reasonable human being, despite the fact that it's pointless.
So
And again, I fully understand that I'm not trying to preach this as a religion or a philosophy. This is what works for me. I've tried other things. This is the only thing that lets me, get up in the morning and have a, semi-decent attitude. Okay? It's not meant to be exportable. I've tried, and I realized it doesn't work. Most people don't react. Most people react poorly to this.
Yeah, I mean, it's very existential. So do you have a similar view on the topic of consciousness? I mean, in all of that's one thing that humans cannot understand from a scientific point of view.
Yeah,
we try it as hard as we can.
Yeah. What's his name? Penrose. Penrose says that the reason we're stuck in physics is because we don't understand how the human mind works, and I think he's dead right on that.
Yeah.
Something is going on with consciousness and how we interact with the outside world. In other words, everything is filtered through our mind.
Mm-hmm.
We need to understand how the mind works to make, I think, real progress in getting to maybe, if not truth with a capital T, something a little closer.
So Penrose,
and I don't know if we're any closer than we were, 30 years ago.
Yeah, I don't know if we are. Well, maybe with AI. I mean, that's a totally different conversation. But
these multi-language models,
large language models, yeah,
that's not the way to go. That's not AI.
Well, neural net. I was referring to more like neural networks.
Yeah, perhaps, but I think with AI, I mean, I don't know. Look, I mean, it's like us having a discussion about badminton, which I know nothing about.
Right.
So I know nothing about AI.
We'll leave that for a more technical AI conversation.
Yeah. But I am not impressed with AI at the moment.
I see.
I am not at all.
And I think Penrose, he holds the view that consciousness cannot be a computation. So there must be something external going on.
Well, again, this is putting physicists ill at ease, because when you talk about consciousness, you're talking about an emergent phenomenon.
Right.
The greater the result is greater than the individual parts.
Right. Not something physics deals with.
That's right. We go the other way.
Yeah.
Imagine the great joke. Imagine the spherical chicken, right? Which you should explain to your viewers if they don't know it. It's a great joke.
Well, the spherical cow in physics is
spherical cow. Yeah.
Right. We make these models that are simpler than the actual cutting edge models, so that we can do things with them. So when you're an intro physics student, you learn Newtonian mechanics. And Newtonian mechanics is a spherical cow model, a simplified model of the more complicated Lagrangian mechanics. And then, well, it turns out things aren't nearly as deterministic as we thought. So that's actually a spherical cow of maybe a quantum mechanical approach. And then you go up the ladder. And the goal is that we're aiming towards, I think in my estimation, the goal is that there's some amount of predictive power that we can gain from these models. And the scale decreases by which we can consider how effective the prediction is. So basically the decimal place increases as we refine our model. But I mean, and we talked about this already, does that mean we're converging on something true, or true with a capital T? That might not be the goal even.
Yeah, we would like to, we hope that that's the case. But even if it isn't the case, let's say that at the end of the day, 1,000 years from now, there's still no progress. Quantum mechanics is still a statistical approach to nature, and general relativity is a deterministic approach to nature, and and that's it. And we can't get anywhere. Okay, will it all have been for nothing? No, no. Those ideas have brought us. I mean, all our technology.
Right. We're in a building.
So we computers, video equipment. We can build an H bomb. I keep going back to the H bomb because one of the saddest things I've seen in teaching introductory courses, science courses to people, is a lot of people think that science is basically some guy over the weekend, some mad genius over the weekend, tinkering in his garage, and lo and behold, he's invented the transistor. And it's like, that's not how it works at all. Okay, you can't build an H bomb in your garage by accident. You need to first develop quantum mechanics and understand how these things work, and then you have to apply a whole bunch of other physics and a whole bunch of people actually to try to get it to work. Okay, so yeah, even if these are not the truth with a capital T, they lead to tangible achievements, and it's hard to believe that there isn't some nugget of that there isn't some reasonable approximation to reality in these theories. It may not be reality, but there's some reasonable approximation, because again, you can't build an H bomb by accident.
Right.
If quantum mechanics had nothing to do with the way nature works, then you effectively have built an H bomb by accident, which makes no sense to me. So yeah, somehow an approximative model that may not be quote unquote the real thing, whatever that is, can still lead to tremendous achievements. So even if we never get there, or even improve significantly beyond these ideas, they were still worthwhile.
I agree. Well, it's been a pleasure talking with you today.
Great.
And as per starting the tradition, if you could sign the
Sure, it'd be
question
a
sheet.
pleasure. And this was a lot of fun for me, Will.
Yes, of course. I'd love to have you back sometime.
Sure. My signature is a little bit of a...
Oh, it's beautiful. Much better than mine. Dr. Magnani, thank you so much.
Call me Loris, Will.
Loris.
One of the best things about retirement is if I say something stupid, what are they going to do? Fire me?